In this section, we're going to take a look at sequences, and we're going to do some calculations with sequences. Now, a sequence is defined as being a function whose domain is the set of positive integers, meaning you're just plugging in 1, 2, 3, 4, 5, so on and so forth. And then you can do that forever, but you're only plugging in positive integers. Oftentimes, we think of a sequence as a list of terms because when I plug in 1, I get an output, which is my first term. I plug in 2, I get an output, which is my second term. I plug in n, and I get an output, which is my nth term. And these list of terms are often called A1, A2, A3, AN, where A sub n is just the nth term of the sequence. It's what you get out when you plug in the positive integer of number n. There are a couple of different ways to write sequences. One of the ways that I can list off all of the terms of the sequence is to list a function value for each term of the sequence. So the nth term is given to you by some function where I plug in the number n. I call this the function notation for a sequence. You can also define a sequence recursively, where in this case, I set my first term equal to a number, and then every next term is going to be determined by a function of the previous terms. So I let my first number be, let's say, the number 1, and then my second number is double the previous one. That would be a recursive definition of a sequence. So we can have the function definition or the recursive definition of a sequence. Oh, by the way, sometimes you have to list off not just the first term, but sometimes you have to list off the first few terms, and then the function that gives you your next term involves 2 or 3 or 4 different previous terms. The function notation of a sequence can be written in a couple of different ways. One is we can just put like curly brackets around a function, around an expression, or sometimes people will put a sub n is equal to that expression. So for example, if my function is 2 times n, I can write it with squiggly brackets around 2n, or I can write it as a sub n is equal to 2 times n. Now, if I plug in an n of 1, 2 times 1 becomes 2. If I plug in a 2, I get 2 times 2, which becomes 4. If I plug in a 3, 2 times 3 becomes 6. Plug in a 4, you get 8. Plug in a 5, you get 10, and so on and so forth. So the terms in the sequence would start at 2, then be at 4, 6, 8, 10, 12, 14, and then again, that pattern would go on forever. So that's, again, a couple of different ways that we're going to see to write the function notation, either brackets around an expression or a sub n is equal to that expression. On occasion, there'll also be the notation where it says f of n is equal to the expression, but these two are more common. And sometimes it'll have curly brackets, and then on the inside there'll be a sub n, and then equaling curly brackets, whatever the expression is. In this case, it'd be 2n. So if we have this function notation, then what we can do is we can find the terms in the sequence by just plugging in values into the n. Let's do that here in example 1. We have 4 sequences, and we want to find the first 7 terms in each of these 4 sequences. In this first example, where we have n over n plus 1, if I plug in the number 1, I'll get 1 over 1 plus 2, 1 plus 1, which is 2. So the first term is 1/2. The second term is going to be what you get when you plug in 2. And you'll notice that there's a pattern here. Obviously, each time I plug in my positive integer, that positive integer is going to go on top. And in the denominator, we're going to get 1 more than that positive integer. So I get 1/2, and then 2/3, and then 3 over 4, and then 4 over 5, and then 5 over 6, and then 6 over 7. That gives me 6 terms. If I want 7 terms, I go 1 more. 7 over 8 would be the 7th term. And then that pattern would go on forever if I wanted it to. So 1/2, 2/3, 3/4, 4/5, 5 over 6, 6 over 7, 7 over 8, etc., etc. In this next example, notice what's going to happen. -1 to the nth power is going to be a -1 when n is 1. So my first term is going to be 2 plus -1. 2 plus -1 is just a 1. My second term, when I square -1, I get a positive 1. Therefore, I get 2 plus positive 1, which is a 3. When I use the exponent of 3, so when I plug in a 3 into n, -1 to the third power is still -1. And I'll get 2 plus -1 again, which is again 1. When I plug in 4, -1 to the fourth is a positive 1, so that's just 2 plus 1, which is 3. When I plug in a 5, I get 2 plus -1, that's a 1. Notice that every time I plug in an odd number, -1 to the odd power becomes -1. Add 2 to that, and I get a 1. Every time I plug in an even number, -1 to an even power is a positive 1, so I end up with 2 plus 1. Therefore, my sequence just goes back and forth between a positive 1 and a positive 3. So 1, 3, 1, 3, 1, 3, 1, 3. I guess that's 8 terms, but we see the pattern. In this sequence, when I plug in 1, the numerator is going to be 1 squared, which is 1. The denominator is going to be 2 to the first power, which is 2. When I plug in 2, I get 2 squared over another 2 squared. So 4 over 4. If I wanted to simplify that, I could. I'm not going to right now, this instant. When I plug in 3, I get 3 squared. 2 to the third power is 8. Then I'll plug in 4. 4 squared is 16. Also, 2 to the fourth is 16. So I end up with 16 over 16, which is again 1 if I wanted to simplify that. I don't want to right now. When I plug in a 5, I end up getting 25 over 32. That's 5 squared divided by 5, 2 to the fifth power, excuse me. 5 squared over 2 to the fifth power. When I plug in a 6, I get 36. That's 6 squared divided by 2 to the sixth power, which is 64. And when I plug in a 7, I'll get 7 squared, which is 49, divided by 2 to the seventh power, which is 128. So those are the first 7 terms of that sequence. Now you'll notice on this one, we kind of started at 1/2. We went up to 1, we got a little bit higher than 1, and then we went back down to 1, and then we're slowly getting smaller and smaller and smaller. So this is nearly 1/2, and this is under 1/2. Now for this last sequence, we have to know what this symbol is. This n factorial, or excuse me, this exclamation point is a factorial symbol. And n factorial means that I take every integer, every positive integer from n down to 1, and I multiply them all together. So for instance, if I would have 5 factorial, that means I take 5 times 4 times 3 times 2 times 1. And if I were to do 6 factorial, then I'd say 6 times 5 times 4 times 3 times 2 times 1. And if I wanted to do 7 factorial, then I do 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, one little weird thing about factorials work whenever we have positive integers. We also allow it to work on 0. We don't need 0 for this problem, but I do want to say that 0 factorial, we say 1. That's because the identity under multiplication is 1. And therefore, you're saying, what if we're not multiplying any integers together? Then the identity becomes 1. So if I have positive integers or 0, I can apply factorial to that and get a 1. And that's the same as 1 factorial. 1 factorial is just 1, not multiplied times anything. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. Notice that all of the factorials below 7 are embedded into the formula for 7 factorial. So if we plug in a 1, 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1. 3 times 2 times 1 is a 6. 4 factorial goes 4 times 3 times 2 times 1, which is 24. Notice that at each step, we're multiplying by one number higher. So 1 times 2 is 2, times 3 is 6, times 4 is 24. And then 5 factorial, I can either do the whole 5 factorial, or I can just take 24 times 5 and get 120. When I multiply by 6, I get 720. That's 6 factorial. And then when I multiply by 7, I get 5,054. Oh, I'm sorry, 5,040. Excuse me. Notice that factorial, while it kind of starts out pretty slow growth the first couple of terms, it gets really fast growth as we move up. So that's a very fast growing sequence. By the way, there is a way to do factorial on your calculator. All you have to do is hit the math menu and then go into probability on the TID4. And then number 4 is the exclamation point. So in the home screen, if I was to do 7 factorial, I just hit 7 and then go math probability. Number 4 on my calculator is the factorial symbol. And you should get 5,040. So this is how we find the first few terms. If our sequence is in the function notation style, whether it's in this written out this way or written out as a sub n is equal to the function notation style. Now we can also do the same thing with recursive sequences. We can find the terms here. So for instance, if I said, here's one sequence, A1 is equal to 2, and then A sub n is equal to 2 times A sub n minus 1. That just means the nth term is twice the previous term. Or in this case, the nth term is the previous term plus the previous term before that, the n minus 1 term plus the n minus 2 term. And then this one has to start out by giving you a couple of numerical values to start with. All right, so let's do these. First term of this first one is a 2. My second term is going to be called A sub 2. And so A sub 2, I know, is equal to 2 times the previous term, A sub 1. That's what n minus 1 is. So if I plug in a 2, I get A sub 2 minus 1, which is A sub 1. I know that A sub 1 is the number 2, so 2 times 2 is a 4. The same thing is going to happen now that I've established my second term. Now I can find my third term. My third term is going to be, based on this formula, 2 times the A of the previous term. So 2 times A sub 2. Double the second term is an 8. Then the fourth term is going to be double the third term. Doubling 8 gives you 16. And then you can see where this is going. The fifth term is going to be double the fourth term. Doubling 16 gives you 32. Starting looking for the sixth term, we're going to double 32. So doubling the fifth term, we get 64. Then when I go to the next term, I double that, and that'll give me a 128. And I think that's the 7 terms that were asked for. So each term is double the previous one. That's what we mean by a recursive definition. Now let's go to this one. First term is 1. It tells us that. Second term is 1. It tells us that. And then I get my third and beyond terms by this expression. My third term is going to be, when I plug in 3, I get a sub 2 plus a sub 1. So my third term is a sum of the previous 2. 1 plus 1 becomes 2, so 2 is my third term. When I look for my fourth term, it's a sum of the previous one plus the one before that. Notice that it's the sum of the 2 previous terms. So in this case, that's a 1 plus a 2, or 2 plus 1, which gives me a 3. We don't add an extra a1 in there. We just say a3 plus a2. The fifth term in this sequence is a sum of term 4 and term 3. 2 plus 3 gives a 5. The sixth term in the sequence is a sub 5 plus a sub 4. That's 3 plus 5. That gives you an 8. And then the seventh term in the sequence is the sixth term plus the fifth term. 8 plus 5 gives you a 13. So those are the first 7 terms of that sequence. By the way, the next term would be 21, because 8 plus 13. And then 13 plus 21 would give you a 34. And then 21 plus 34 would give you a 55. And you'd keep going on like that for a long, long time. And while this starts out pretty slow, it actually, as you get some really high terms, it grows pretty fast eventually. By the way, this sequence here, 1, 1, 2, 3, 5, 8, 13, 21, that actually has a special name. That's called the Fibonacci sequence. All right, and it's a really famous sequence in mathematics. Again, I'm not going to go through why the Fibonacci sequence is, there's a lot of interesting things to go about with the Fibonacci sequence, but again, that's what it is here. Instead of taking my time on this video to do that, what I'll do is I'll move on and try to look at the first few terms, and then determine the function of the sequence. In other words, find the expression that gives the sequence if I know the first few terms. Basically, what we're doing is the reverse of what we just did in example 1. Now, this is saying we want to find the function of the sequence. So we want to find the expression, like the f of n, that gives us the nth term. We don't want to find, this is not asking for the recursive of what we're doing. We could do that as well. So let's take a look at these two sequences and try to come up with a function that gives me these sequences of numbers, or functions that give me these sequences of numbers. I'll have one function for this first one and another for this second one. For this first sequence, notice that when we're going from term to term, we're always adding 3, 2 to 5. So when we go from term to term, we're adding 3 each time, okay? And we're starting with a sub 1 being the number 2. Now you could do a recursive definition with that, but I want a function definition with that. So if we're adding 3 each time, that means the nth term is what you're going to get when you take 3n plus some number. And I'll call that number for right now b until I can know what exactly it is. Adding 3 over and over and over again just means I'm going to go 3 times n, because each time I increase n by 1, that adds another 3. So this is like a linear expression, 3 times n plus b. Now, in order to find the b, we just need to realize that a sub 1 is equal to 2. So that means that when we plug in 1, 3 times 1 plus b has to be equal to 2. So a sub 1 needs to be there. So 3 plus b equals 2, which means that b has to be negative 1. So you can solve this equation for b, and it has to be negative 1. Again, when I say this equation, I have 2 equal signs here. Since a sub 1 is 2, that has to be the same as what you get when you plug in n of 1 in there. Usually I'd probably do this underneath. And then we get a b of negative 1. And so that means my function expression that gives me my sequence is 3n minus 1. Again, I can either write that as a sub n is equal to that expression, or I can take squiggly brackets and write 3n, minus 1 inside the squiggly brackets. Either way is perfectly fine. I tend to, just me, I tend to write the a sub n is equal to. Now, if I go to this one, we have 5, 10, 20, 40. It looks like it's doubling each time. So each increase by n is multiplication by 2. And also, I can see that my first term is 5. Sure why that's doing that. So first term is 5, and we're doubling by 2 each time. So that means my nth term is going to be given to me by some constant number. I'll call it, I guess I'll call it C this time. Doesn't matter what you write. And doing this repeated multiplication by 2 means that we're going to take 2 to the nth power and then times it by some constant number up front. I know a sub 1 is 5, so that means when I plug in a 1, five is equal to C times 2, which means C is 5 halves or 2.5. Now I know what what my sequence looks like. The nth term in my sequence is equal to 2.5 times 2 to the nth power. Notice that repeated addition becomes a linear function. Repeated multiplication becomes an exponential function. So we get an exponential function there with base 2 because we're doubling each time. When we add 3 each time, we get a linear function whose essentially the slope there is 3. So again, repeated multiplication, think exponential. Repeated addition, think linear. Now here are 3 sequences that with the tools that we've done so far, you can figure out. If you want to try to find the function for each of these 3 sequences, meaning each a function for each one of the sequences, then go ahead and do that. Push pause on the video and try that on your own. In a couple of seconds, I will do that on this video. All right, with this one, this first one, we are adding 6 each time. And a sub 1 is once again equal to 2. So the adding 6 tells me that my nth term is going to be 6n plus some number. And then I can find that number if I decide, well, if I notice that my first term is equal to 2, then 2 has to be equal to 6 times 1 plus b, which means b has to be a negative 4. So therefore, the nth term in this sequence is going to be given by 6n minus 4, by the expression 6n minus 4. This second sequence is a little bit different because first off, we have a 1 over there. I'm going to write that as 1 over 1 to make it a little bit cleaner so that all of our terms are fractions. Now what we can see is that the numerator is alternating back and forth between a positive 1 and a negative 1. The denominator, 1, 4, 9, 16, 25, is just n squared. So it's just the squares of n. Now here's the thing. If I plug in a 1, I should get a positive 1 in the numerator. When I plug in a 2, I should get a negative 1. That's the opposite of what happened in the case where I had negative 1 to the nth power. So negative 1 to the nth power alternates in such a way that when you plug in odd numbers, you get a -1. And when you plug in even numbers, you get a +1. I want the opposite to happen. I want it so that when I plug in a negative number, or excuse me, let me rephrase that. I want it so that when I plug in an odd number, I get positives. And when I plug in an even number, I get negatives. The way I do that is instead of using the exponent of n, I use the exponent of n plus 1. So -1 to the n, when I plug in odds, gives me negative. -1 to the n plus 1, when I plug in an odd number, +1 will make it even, and so I'll get a positive. -1 to the n, when I plug in an even number, -1 to an even power gives me +1. If I plug in an even power here, I get -1 to the even plus 1. That's going to be an odd power, so I get a -1. Hopefully that makes sense. In essence, my nth term, therefore, becomes a fraction. The numerator of that fraction, in order to start getting positives with odd powers, negative with even powers, I need to use the -1 to the n plus 1 version. Oh. And then in the denominator, that's just n squared. So that is the function expression that gives me all of the terms in this sequence. Now for this last sequence, this is kind of tough to see unless you've seen it before. It turns out if you rewrite these as factorials, 2 is actually 2 factorial. 24, we saw earlier, is 4 factorial. 720 is 6 factorial. It turns out 40,320 is 8 factorial. And 3,628,800 is 10 factorial. So if I rewrite these as factorials, which again is hard to see, then it becomes clear what my sequence should be. It should be even numbers factorialed. Now, if I just want the even numbers to be factorialed, one way to do that is to make sure that whenever I plug in a 1, I get a 2. Whenever I plug in a 2, I get a 4. Whenever I plug in a 3, I get a 6. When I plug in a 4, I get an 8. In other words, I plug in a number, multiply it times 2, and then take the factorial of that number. So this would be 2n factorial, where the 2n is inside parentheses. By the way, just so that we're all on the same page, this is not the same thing as 2 times n factorial. 2n quantity factorial is not the same thing as 2 times n factorial. Factorial kind of works like an exponent. You have to do that before we multiply. And so these are not the same thing. So be careful to have parentheses around the 2n in this example. But there you go. So that is the expression for the expressions for these three sequences. Now, I do want to say one thing. Basically, all sequences can have a closed function form, even if they're written recursively. So back when we dealt with these recursive sequences, we found the terms of this first one to be 2, 4, 8, 16, 32, 64, 180, 128, and so on and so forth. If I simply wanted to write a function version of that sequence, it's just 2 to the nth power. 2, 4, 8. 2 is 2 to the first power, 4 is 2 squared, 8 is 2 to the third, and so on and so forth. So some of our recursively defined sequences have really easy function versions of them. Other times, the sequence's function version can get really, really messy. For instance, the Fibonacci sequence, if you derive the formula for this, it takes quite a lot of work. But the Fibonacci sequence is a really messy looking expression. It turns out it's 1 plus the square root of 5, all raised to the nth power, minus 1 minus the square root of 5, all raised to the nth power, divided by 2 to the nth power, multiplied by the square root of 5. And it turns out if you plug in 1 into this big ugly mess, you get 1. And if you plug in 2, you get a 1. And if you plug in a 3, you get a 2. If you plug in a 4, you get the number 3. You plug in the 5, you get the number 5. You plug in 6, you get a 7, you get an 8. You plug in a 7, you get a 13, and so on and so forth. And again, how you would come up with this is well beyond the scope of this class, but that's what it would be. And it turns out sitting inside of that is 1 plus root 5 over 2, which is the so-called golden ratio. So golden ratio, I'll just write that down, is the fraction 1 plus the square root of 5 over 2, which is approximately 1.612, something like that. So 1.61 or 62. I'll go 1.618 is what I'll write down. Okay. So that's the golden ratio, and it's sitting inside of the Fibonacci sequence. This is a really, again, well-known sequence. But now, obviously, you're not going to be coming up with that formula for a sequence like this, but for a sequence like this one, you could absolutely come up with 2 to the nth power. And for the ones that we had just done, obviously, we can come up with the formulas, the closed formulas for adding 6 to each term, or squaring squaring pieces, squaring ends, alternating between -1 and +1, depending on whether we start with a -1 or if we start with a +1. Factorial, again, probably wouldn't see that off the top of your head, but that's what that is. So that's how we find the terms of the sequence, and we find the explicit expression that gives us the terms of the sequence. Now, the other very important part of this section is finding limits of sequences. Now, I said at the beginning, a sequence is a function. Therefore, the limit of a sequence is the limit of a function. And because the sequence just goes on and on and on forever, the ends keep increasing. When we talk about the limit of a sequence, we're talking about the limit of a function as n grows to infinity. So that's it. The limit of a sequence is the limit of the expression as n goes to infinity. Now we have to be a little bit careful here because our n's, the ones we're plugging in, are all going to be positive integers. So when we do the calculations, um, hopefully we have continuous sequences, or excuse me, continuous functions, but sometimes we don't. And we have to take that into account. Now, when a sequence has an actual real number limit, let's say the limit of the sequence was 47, then we would say that the sequence converges to 47. Whatever that real number limit is, the sequence converges to it. And we say the sequence diverges if the limit of the sequence either does not exist or is positive infinity or is negative infinity. So if the limit doesn't exist, or if it's plus or minus infinity, then the sequence diverges. So converges means has a real number limit. Diverges means the limit does not exist or goes off to infinity. Let's go back to our original four sequences and let's think about what these four sequences do. Do they converge? Do they diverge? If they do converge, what do they converge to? They're not all going to do the same thing. There's a couple of different ways to determine the limits. One of them is to write out a bunch of terms and then just use common sense to determine what they are. In this first case, we have n over n plus 1. That is that gives us these 7 terms. And you might be able to see that as these things, as n grows, each of these terms is getting closer and closer and closer to the number 1. Imagine that we plugged in the number 800. We'd have 800 divided by 801 as the term. That's pretty darn close to 1. Or if we plugged in 10,000, we'd have 10,000 divided by 10,001. Again, that's pretty darn close to 1. So we can just logically think through that. Or we could say we're using a limit as n goes to infinity of n over n plus 1. And I can use all of the tools that we know with functions, just like when I took the limit as x goes to infinity of x over x plus 1. This is a rational expression. So let's change this just to x so it's a little bit more familiar feeling. This is a rational expression. So I would take the coefficient of this, divide by the coefficient of this because they're the same power, and that's 1 over 1, which is 1. Therefore, the limit of this first sequence is 1. So either way, using common sense and logic, or by using the tools of limits that we've developed earlier, we can say that the limit of this sequence is 1. So we would say that this sequence converges to 1. That's the language we use. The sequence converges to 1. Now, in this next one, I can't really do any algebraic tricks to this because -1 to the n is not going to be a continuous function over the real numbers. I can, if I want, whoops, I can, if I want, sorry, write this out as 2 plus -1 to the n, but my tools from previously when I found limits don't help me as much because the only n's I can plug in are positive integers. But I can see that this sequence is just going back and forth between 1 and 3. If it goes back and forth between 1 and 3 forever, then it doesn't ever converge. So in other words, the limit of that sequence does not exist. Since the limit of that sequence does not exist, we say this sequence diverges. So that first one converged to 1. The second one diverges. How about this third one? Once again, in this case, the tools of algebra will actually work out pretty nice. We're going to take an n squared divided by 2 to the nth power. Here we can actually use L'Hopital's rule because I get the indeterminate form infinity over infinity. So I can, again, use L'Hopital's rule. L'Hopital's rule would say 2n divided by 2 to the nth power multiplied times natural log of 2. And then I would still get the form infinity over infinity. And I could use L'Hopital's rule again. Limit as n goes to infinity. Now we'd have 2 over, again, this is the derivative of the top. Derivative of n squared is 2n. Take another derivative, you get 2. If I take a second derivative of the bottom, I get 2 to the nth power times 2 copies of natural log of 2. Notice what's happening now. The top is staying still. The bottom just goes off to infinity. So this is the form 2 over infinity, which means my limit there is 0. So denominator grows. So the limit of this sequence is 0. And we would say that the sequence converges to 0. Lastly, it's pretty easy to see what's happening here. Now, like this first one, not the first one, like the second one, the algebra is not going to work super nice because factorial is not really a continuous function. Factorial is defined well on the positive integers, not so much on, you can define it on other real numbers, but it's harder to do so. So we're just going to define it on the positive integers. But it's pretty easy to see that n factorial just keeps growing and growing and growing. So as n gets bigger and bigger and bigger, this sequence is going off to infinity. And that's the scenario in which we say that the sequence diverges. Some would say diverges to infinity as well. Sometimes I say that, sometimes I don't, but that's opposed to this one, which doesn't exist. So this one diverges because it doesn't exist. N factorial diverges because it goes to infinity. Again, some people would say diverges to infinity on that one. These four show you a lot of different techniques. Obviously, we can use L'Hopital's rule if we have nice continuous functions like n squared and 2 to the n dividing. We can use our rules of rational expressions like we had before. We can just look at the numerical values and see that they don't ever meet up, that they don't ever get closer to a single number. They're getting just going back and forth. And then we can look at numerical values and see that they grow forever. So these four are, again, good representations of what could happen. We could converge to a real number. We could diverge because the limit doesn't exist. We could diverge because it goes off to infinity. We could converge to zero. Lots of other things too. Now, the biggest tools that we are going to use are just what I did. Common sense, looking at the sequence, seeing that it goes off to infinity or that it goes back and forth between numbers. That's fairly common sense. Using the tools of algebra that we've developed before and the algebra of limits. Those are the big tools that we're going to use. So mostly we're going to use the tools that we've previously seen to deal with the limits of the functions. In particular, if the expression for the nth term in a sequence is given by f sub n, and if f of x is a continuous function over the real numbers, then I can just say the limit of the sequence works just like the limit of the function. Now, the reason for that is basically if you think of a sequence as a function from the positive integers onto the real numbers, you can think of it as just a series of points whose x value is a positive integer. So I plug in 1 and I get a y value of some number, which is a sub 1. I plug in 2 and I get a y value, which is a number a sub 2. So for instance, if my function is 1 over n, 1 over 2 is 0.5, 1 over 3 is 0.333, 1 over 4 is 0.25. So if my function is 1 over n, then I get these points. 1 over 1 is 1. 1 over 6 is 1/6. Obviously, they're giving me the decimals. 1 over 5 is 0.2 or 1/5. And then I get basically a collection of points. Well, if I take 1 over n as my y value, I could have easily graphed f of x is equal to 1 over x. And you can see that these points for my sequence all pass through the function f of x equals 1 over x, or the function passes through each of those points. And so they're going to do the same thing as we move out further and further away from the y-axis. They're going to both go towards the same number. Now, obviously, if it's a different function, if f of x is equal to x, then it's going to not go, maybe not have a limit, but you can see what's happening. It's going in the same direction. That's the point. So if we have a continuous function over the real numbers that is determining the terms in my sequence, then the limit of that function as x goes to infinity is going to be the same thing as the limit of the sequence. I think that's fairly obvious and intuitive. So that's one big tool, and that allows us to use all of the tools of limits of continuous functions that we had before, especially the limit as x goes to infinity, or now we're using the variable n, so the limit as n goes to infinity. There are other tools as well that we can use. We won't use these quite as often as just our standard techniques for finding limits, but one of the tools that we can use is called the squeeze theorem. This says if we have two sequences which are converging to the same limit, and there's also a third sequence where maybe it doesn't start out in between, but at some point, that third sequence is always in between the other two. The terms of the third sequence is always in between the first two. So we have a limit of sequence A sub n and a limit of sequence C sub n. And we're saying after a while, B sub n sequence has terms always between A sub n and C sub n. Well, if the first two have limit L, then the middle sequence also has to have limit L. That's fairly straightforward if you visualize in the same way we visualize on a graph, the visualization of the sequence with these continuous functions. So the graph of f of x equals 1 over x you see here, and then you see the points that give you the sequence 1 over n, a sub n equals 1 over n on that graph. Now, this limit as x goes to infinity is 0. Also, if I look at 1 over x squared, or the sequence 1 over n squared, I get this. Now let's pretend I want another sequence, and my other sequence is going to be 1 over x to the 1.2 plus, let's say plus 3. Okay. It starts out a little bit under these other two sequences. But once we get to the third term, this sequence, 1 over x to the 1.2 power plus 3, is always in between the other two. So if I know that the other two both have a limit of 0, then I know the in-between sequence also has to have limit of 0. Even though it might not originally start out in between for the first couple of terms, by the time we get to the third term, it's always in between. And therefore, since it's always going to be in between from 3 and beyond, if I know that the top sequence has limit 0 and the bottom sequence has limit 0, then the in-between sequence is going to also have limit 0. Now, it doesn't always have to be 0. Obviously, some sequences we could move everything up, shift everything up by, let's say, 2. And we could figure out that this top sequence has limit 2, the bottom sequence has limit 2, and therefore the middle sequence also has to have limit 2. And I don't have to actually do the algebraic work on that middle sequence. So if I know the top and the bottom both have limit 2, then the middle sequence has limit 2 as well. So that's the idea of the squeeze theorem. Now, one important offshoot of the squeeze theorem is going to be what we call the absolute value theorem. If we have one of these sequences that alternates back and forth between positive and negative values, if we take the limit of the absolute values and the absolute values are going to 0, then the limit of the overall sequence is going to also go to 0. Now, I want to point out what types of sequences we're talking about and what types of sequences we're not talking about. So I want to look at that and talk about what sequences we're talking about and what sequences we're not. This has an alternating component of -1 to the n, where I had 2 plus -1 to the n. So that component is alternating, but the actual sequence is not. In other words, if I took the absolute value of 2 plus -1 to the n, it still doesn't exist because the absolute value of 1 is 1, the absolute value of 3 is 3, absolute value of 1 is 1. It still goes back and forth between 1 and 3, so that limit does not exist. However, the types of sequences that this theorem, this absolute value theorem, is good to deal with are the kinds like this one. We have 1 over 1, -1 over 4, 1 over 9. If I took the absolute value of the a sub n, let's actually just write that down. So absolute value of a sub n, that is going to be the absolute value of this expression -1, oops, -1 raised to the n plus 1 power divided by n squared. Now, if you recall, n is always positive integer. So n squared, the absolute value of n squared is just n squared, since n is always positive. The top just goes 1, -1, 1, -1. The absolute value of 1 is 1. Absolute value of -1 is also 1. So when I take the absolute value of those terms, I get 1 over n squared. Now, we should know that the limit of 1 over n squared, well, 1 over n squared is a continuous function over the real numbers, if I let n be x, and it's going towards 0. Therefore, this sequence, my original sequence, also converges to 0. So my original sequence converged to 0 because the limit of the absolute value of my sequence also converged to 0. This is just one application of the squeeze theorem. Okay, I'll show you what I mean by that. So here's the visualization. What you see here are all these points. When I plugged in, oh, I misdid this. So let me change that. There we go. So what you see is all these points, and the y values are giving you the sequence that I just looked at. So 1 over 1, and then negative 1/4, and then positive 1/9, and then negative 1 over 16, and then a positive 1 over 25, and so on and so forth. And you can see that these bounce back and forth across the x-axis. So these are the points of the sequence that we just looked at that's the alternating sequence. Well, if I took the just 1 over x squared, that sequence would have this continuous curve to it, and you might look at all of the points of that sequence as an upper bound as all of the points on my sequence. So the alternating sequence has upper bound of positive 1 over x squared. It also has a lower bound of negative 1 over x squared. So we have two sequences that provide a positive and a lower bound. One is just the positive parts, one is the negative parts, and these both are converging towards 0. And so if the limit of one of these sequences goes to 0, then I can apply a negative to it. The limit of the opposite sequence goes to 0. And then I have my squeeze theorem where all of my points are in between, although they're technically just sitting on one of these two curves. So we're just getting the squeeze theorem where one side is the absolute value of A sub n, and the other side is the negative of the absolute value of A sub n. And that's what happens. So squeeze theorem with 0, and then we get the absolute value theorem. So just replace the A sub n with absolute value of A sub n. I should say negative absolute value of A sub n on this side, and then a positive absolute value of A sub n on this side, and then negative absolute value of A sub n less than or equal to just the regular A sub n less than or equal to positive absolute value of A sub n. And if both of those have limit 0, which is just the limit of one of those being 0, then the alternating part has to have limit 0 as well. And that's what the absolute value theorem says. If the limit of the absolute value of A sub n is 0, then the limit of A sub n has to be 0. I want to point out that this does not work for any other numbers. The only number that this works for is 0. If the limit of the absolute value of A sub n is 14, then probably the limit of A sub n maybe, well, I should say on some sequences it'll be 14. On other sequences, it might bounce back and forth between negative 14 and positive 14. So it only works with 0. So this is the one we just found the limit of, -1 to the n over n squared. We took the absolute value and the absolute value. Oh, no, we had n plus 1 on our exponent. If I have just -1 to the n, that'll give you the same thing. And limit of 1 over n squared becomes 0. So the limit of this first sequence will be 0 for the same reasons we just expressed. On this one, if I take the absolute value, something weird happens. So like I said, first one, -1 to the nth power over n squared. Take an absolute value of that. All I did was change my previous example from having n plus 1 in the exponent to just having n in the exponent. But absolute value of -1 to the n is still just 1. So we get 1 over n squared. Limit of 1 over n squared as n goes to infinity is 0. So that this sequence converges to 0. This original alternating sequence converges to 0. This second one, like I said, something interesting happens. If I take the absolute value of a sub n, well, basically what you could do is you could take the absolute value of -3 to the n, and you can kind of factor that into, you got to be careful when you factor though. It factors into -1 to the n multiplied times 3 to the n, since -3 is just -1 times 3. But both of them have to have the exponent of n. So basically what we get is 3 to the nth power. Now it turns out 3 to the nth power is not 0. It goes off to infinity, just keeps growing and growing and growing. That does not mean -3 to the nth power goes to infinity. -3 to the nth power actually does not exist, because if you look at what's happening, it's going to be bouncing back and forth between extremely large positive numbers and extremely large negative numbers, meaning in the absolute value sense of the word large. We're going to have -3, then a +9, and then a -27, and then a +81, and then a -243, and then a +729, and then a -2,187, and so on and so on and so forth. So just because this limit goes to positive infinity doesn't mean that this limit goes to positive infinity. This limit bounces back and forth, doesn't exist. Hopefully all of that makes sense. Let's do a couple of other examples here. Let's find the limits to these three sequences. As if you want to, you can pause the video and then do each on your own, and then check and see if you have the same answer as I have. If not, then I will do these three examples in just a couple of seconds. All right, so let's take our first sequence of this example here. A sub n equals 2/3 to the nth power. If I want to take the limit of that, I have to realize that that's an exponential expression and that the base there of 2/3 is less than 1. So the base is less than 1. And when I say the base is less than 1, I mean it's also positive. So technically speaking, if I call if I call the base b, b is between 0 and 1. All right. So the base is between 0 and 1. That means if I raise that power to higher and higher in exponents, my function is going to get closer and closer and closer to 0. Therefore, the limit is going to go to 0 since the base is between 0 and 1. Notice that in the previous example, I had an exponential function where the base was bigger than 1, and the limit of that one went off to infinity. So if the base was 3, it would go off to infinity. But if the base is between 0 and 1, then we're going towards 0. So there we go. The limit of this function is going towards 0. Knowing the absolute value function and knowing how that can work with a negative inside of an exponent raised to the nth power, hopefully we can see that if I take the absolute value of a sub n in this second example, that is simply going to be the expression positive 2/3 raised to the nth power. Now we know that the limit of this goes to 0. Therefore, so the limit of, let me write it this way, the limit of the absolute value of a sub n is equal to 0. And this means, based on the absolute value theorem, that the limit of my sequence, where we have negative 2/3 to the nth power, is also 0. Notice that means anytime the base is between -1 and +1, we're going to have limit of our sequence going to 0 if I have my sequence as just an exponential base raised to the nth power. So now I can say that anytime my base is between -1 and +1, limit of that base raised to the nth power is going to be 0. Now, lastly, for this example, we have cosine of n times pi over 2. This one's a little bit tricky. So let's start listing out some elements. If I plug in an n of 1, I get cosine of pi over 2. Cosine of pi over 2 is 0 over an n of 1. If I plug in a 2, I get cosine of pi. That's going to be -1 over 2. I think I'm going to write it this way. My third term, when I plug in cosine of 3 pi over 2, also gives me a 0 over 3. When I plug in my fourth term, plugging in a 4 gives me 2 pi. So cosine of 2 pi is a +1, and then I get a 4 in my denominator. When I plug in a 5, cosine of 5 pi over 2 is 0. Then when I plug in a 6, cosine of 6 pi over 2 is a -1. When I plug in a 7, I get 0 over 7. When I plug in an 8, I get a +1 over 8. You can see that the numerators have this pattern where we're going to go 0, -1, 0, +1. 0, -1, 0, +1. If I plug in 9, 10, 11, 12, I'll still get 0, -1, 0, +1 in the numerator. And then the denominators are just growing. This is a great opportunity for a squeeze theorem. What I'll do is I'll say that A sub n is between two different sequences, one of which is going to be -1 over n, and the other, we'll call that C, I guess, is going to be a +1 over n. And you can see that my A sub n at the lowest is always -1 over n. At the highest, it's +1 over n. And then sometimes it's just 0. If you do a limit of 1 over n, limit of 1 over n is 0. That is also the case if we're dealing with the limit of -1 over n. That's also 0. So cosine is at smallest -1 and is at biggest +1. So these two sequences bound the sequence I was given. A sub n is always in between B and C. Since both B and C have a limit of 0, that means A sub n also has limit of 0. Obviously, not every sequence is going to have limit 0. We saw some earlier which don't, but in this case, this one has limit of 0. Again, this is just an application of the squeeze theorem because we have this weird numerator that bounces in between 0 and -1 and 0 and +1 all the time. Now, one thing that the book goes over that we typically don't spend a lot of time on is the concept of a bounded monotonic sequence. Bounded simply means that the sequence doesn't get above or below a real number. So it's bounded by L and M if every term never gets below L and every term never gets above M. So if it's bounded, then the sequence is in between two different Y values on the graph. Now, monotonic means it's either always increasing or always decreasing. So monotonic means always increasing. So the terms keep getting bigger and bigger and bigger. Or it's always decreasing. The terms keep getting smaller and smaller and smaller. If the terms keep getting bigger and bigger and bigger, but we can't ever cross over the M, then the sequence has to flatten out on the curve and therefore it's going to converge. If the sequence keeps getting smaller and smaller and smaller, but cannot cross over L, then it's going to flatten out and it will converge. So there is a rule that is given in the book called the bounded monotonic convergence rule that says if a sequence is bounded and monotonic, then it is going to converge. Doesn't tell us what it converges to because it might flatten out before it hits that M. It might flatten out before it hits that L. If it's decreasing, it might flatten out before it hits the L. If it's increasing, it might flatten out before it hits the M. So we can do a couple of those, and we'll also kind of determine whether the sequences are bounded and monotonic. But generally speaking, the bounded monotonic is not as useful for this class because we have quite a number of rules on limits from previous material that we can take advantage of. And the bounded monotonic isn't quite as strong as some of those previous rules. Let's take a look at finding these limits, and then I'll talk if each of them are bounded and monotonic. If you want to do these on your own, obviously you can try these on your own before I do these. If you do want to do that, then push pause on the video. Otherwise, I'll jump right into it. So I want to find the limit of 4 minus 1 over n. So the limit of that sequence is going to be the limit of 4 minus 1 over n. Now, one of my rules of limits that I can use comes from previous rules. I can take if the limit of 4 exists and if the limit of 1 over n exists and are both real numbers, then I can find the limits separately. Limit of a constant number like 4 is just 4. Limit of 1 over n is 0 as n goes to infinity. So this limit, using the algebraic tools that we already know, is 4. Now, I want to say this about this limit, or not this limit, this sequence, excuse me. This sequence is in fact bounded because if you start plugging in n of 1, n of 2, we're always going to get 4 minus this number. So that means the sequence is always going to be under 4. This fraction, by the way, is always a fraction that is 1 or less. So when we take 4 minus something that is 1 or less, the smallest that number can be is 3. This sequence, therefore, is bounded on the low end by 3 and on the high end by 4. It's also monotonic because if you look at two values, a sub n, a sub n versus a sub n plus 1, it turns out the a sub n plus 1 is always going to be greater than or equal to a sub n. And that's just a matter of simple algebra because we have 4 minus 1 over n is always going to be less than or equal to 4 minus 1 over n plus 1. I can subtract 4 from both sides. I'll add 1 over n to both sides, and then I'll add 1 over n plus 1 to both sides. If you rephrase that, 1 over n plus 1 is less than or equal to 1 over n. Okay, again, that's just algebraic work. We know this is true because this is 1 over a smaller denominator. That's always going to be bigger than 1 over a bigger denominator when n is a positive integer. So like 1/2 is a bigger fraction than 1/3. 1/3 is a bigger fraction than 1/4. 1/5 is a bigger fraction than 1 over 6. 1 over 15 is a bigger fraction than 1 over 16. So for every n, that's going to be true. So we have monotonic because that's always true. We have bounded because that's always true. And the bounded monotonic sequence theorem says, therefore, we know this sequence converges. But notice we kind of already knew that because of our nice limit tools that we've developed earlier. Let's take a look at this sequence, this second sequence, 3n divided by n plus 2. I'm going to simply utilize the fact that this is a rational expression, 3n over n plus 2. It's like 3x over x plus 2. And we know if we have a rational expression where the polynomial in the numerator is of the same degree as the polynomial in the denominator, then all I have to do is take the coefficient of the top, the lead coefficient of the top, divided by the lead coefficient of the bottom, and I know that that limit is 3 using my algebraic tools that I already know. So it's those limit tools that I already know. Now, it turns out that 3n over n plus 2 is, in fact, bounded. And also, you can go through the fact that this is going to be monotonic as well. Instead of doing the algebraic work, I'm just going to graph this and show you that it's bounded and monotonic. But you could have also done the algebraic work and decided, like, if you plug in 1, what's happening? As you plug in bigger and bigger numbers, what's happening? And we figure that out. So I'll look at the graph, but you could also do the algebra. So this one, 3n over n plus 2, has these points to the sequence. You can see that the lowest point is 1. You can see that it's growing. It never actually touches 3, so it's actually bounded by 3 and bounded by 1. I'm going to change the... So we're always between 1 and 3 forever as we move towards the right. And then you can see that it's also monotonic, that it's always increasing. By the way, I said it's bounded by 3. It's technically also bounded by any number above 3. So it's also bounded by 5 because as you move to the right, we never cross over 5 either. So it's bounded between 1 and 5, and the limit is 3. It's also bounded between 1 and 700. And on the lower end, we could say it's bounded, by -3 and +9. Any numbers where the numerical terms don't ever get above or below those numbers, we're bounded by. So bounded, yes. Monotonic, yes, because as you can see, we're always increasing. So a sub n is always a little bit smaller than a sub n plus 1. So bounded monotonic is going to force us to flatten out. And in this case, it flattens out at 3. Oops. So bounded, again, the a sub n's are bounded. Again, you can use any numerical value. You can use -2. Anything that's less than 1, it's bounded by that below. And anything that's greater than or equal to 3, it's bounded by that above. Let me just use the closest bounds that we can get, though. I'll use the close bounds. And then, like we said, it is monotonic. You could go through the algebra, but we just saw that a sub n is always smaller than a sub n plus 1. Smaller than or equal to is monotonic, so we're good to go. Here's another one. Here's a sequence 5n times e to the negative n power. I may rewrite this as 5n over e to the nth power. That's going to be easier to apply my limit to. This is a continuous function. And right now it has form infinity over infinity. If I use L'Hopital's rule, L'Hopital's rule will give me that the limit of my sequence is the same as the limit of 5 over e to the n. As e to the n, as n grows, e to the n grows, 5 stays the same. And so we get limit of this is 0. We probably would have figured that out because this is a linear growth on top, and this is an exponential growth on bottom with base bigger than 1. And anytime we have linear versus exponential, exponential growth is going to grow faster than linear growth. So the denominator grows faster. So the sequence has limit of 0. If I wanted to think about bounded and monotonic, this one is bounded. It turns out on top, if the highest term you get is when you plug in 1, you get 5 over e, which is approximately 1.84. But on the bottom, this is never a negative number. Remember, we're plugging in positive numerical values in for n. So on bottom, each term, each a sub n, is always bigger than 0. It's always positive each term. And then it's bounded above by this weird 5 over e. And sometimes people might not like 5 over e, so you can pick something that's like just bigger than 5 over e. You could pick something like 3, for instance. This one is also monotonic. Algebraically, it's a little bit tougher to deal with. It's not bad at all, though. I will actually go through this one algebraically. Let's take 5n over e to the nth power and look at it versus 5 times n plus 1 over e to the n plus 1 power. we'll look at this versus this, and then we'll put the correct less than or equal to versus greater than or equal to on that. And essentially what I'm going to do is I'm going to rewrite my right-hand side. If I'm doing this algebraically, you don't have to do this algebraically. You could also graph it. But my right-hand side is going to be 5n plus 5 over e to the nth power times e to the first power. It turns out if I multiply both sides by e to the nth power, then both those denominators go away. So multiply times both sides by e to the n, I'll get 5n versus 5 over e times n plus 5 over e. I'm multiplying and then dividing both by e. And then I can just like subtract 5 over e to the nth power. Not to the nth power, excuse me. Subtract 5 over e times n. So I'm getting 5 minus 5 over e times n on the left versus 5 over e. Now, when n is bigger than 1, 5 minus 5 over e is going to be bigger than 5 over e. So this left-hand side is always going to be bigger. Now we subtracted 5 over e, so that doesn't change the symbol. Multiplying by e to the n power doesn't change the symbol, that's positive. Simplifying doesn't change the symbol. And that means that in this case, a sub n is always greater than or equal to a sub n plus 1. So that's the algebraic. That's a long algebraic explanation. But for all n, this side is bigger than this side. So it is monotonic. So all three of these examples, first off, gave me limits that I could do algebraically, and were also bounded and monotonic. Now, not everything is going to be bounded and monotonic. In fact, we saw a couple of things which were not bounded or monotonic. For instance, this sequence that we saw earlier, where we had -3 to the n, was neither bounded nor monotonic. -3 to the n shot off to positive and negative infinity back and forth. So it was not bounded because it goes off towards infinity if it's positives, and if it's negatives, it goes off to negative infinity. And the limit did not exist. So in this one, we're not bounded and not monotonic. This one was actually bounded. This one is bounded. Well, one way you could bound it is between -1 and 1. Not the only way you could bound it, but it's going to be bounded, but it was not monotonic. So notice that this was bounded but not monotonic. It still had a limit that was a real number. By the way, it's not monotonic because every other one is going to be positive or negative. And so we're going to be bouncing back and forth between numbers which are bigger and smaller than 0. So this was bounded but not monotonic, still had a limit. This also is bounded but not monotonic. It's bounded again by -1 to 1, and it's not monotonic because we can see we're going from 0 to a negative number to a 0 to a positive number to 0 to a negative number, 0 to a positive number. So we're bouncing back and forth. So my point of this is twofold. Bounded monotonic sequences always are going to have limits. But you can still get limits if your sequence is not monotonic, like in these two examples. If your sequence is not bounded, then your limit probably is going to be infinite or does not exist. And so the limit might go off to infinity, might not exist. So there's just because it's not bounded or not monotonic, well, I should say just because it's not monotonic doesn't mean it doesn't have a limit. We're saying if it is bounded and is also monotonic, then it will have a limit. But if it's not monotonic, it may also have a limit, but it may not as well. And that's where the tricky part comes in. So lots of different examples, lots of different things. Most of the time, we're going to be using the algebraic techniques that we've developed about limits earlier. And that's probably the most important part about finding the limit of sequences. Remembering those algebraic techniques that we've developed earlier about limits. So that's the end of this first video on sequences.